feature in DCLD now, or let's say one improvement, which helps you to chase these kind of problems more specifically. So if you look at the loop, most of the loops or the Bode plots are always starting at somewhere at 10 hertz or maybe 100 hertz. So there the loop always looks super nice and easy. But what is really interesting is if you look into the low frequency range, there you see that something's happening to the gain and the phase. And that is normal for any kind of digital controller. So let's start with this smallest possible number space here, single bit shifting. So if you look at the gain, it's coming down to maybe 50 hertz, and below 50 hertz, there is no the control loop stops working. It does not really respond or change its response to any incoming change in that frequency range. So if you have low frequency components or transients hitting your control system, they're just passing through, and the controller will not really respond to them. And that might really be a problem, because this is one of the things you might often encounter in customer designs, is that the loop starts to generate low frequency oscillations, maybe 10 hertz, 5 hertz, some weird, I don't know. It's never serious, but it's weird. And that is one of the reasons actually why this happens. So by changing the number space and adapting it to the final design, you can improve that region. So if you go up to what DCDT is using, it's getting slightly better. Then dual bit shifting is again making a huge improvement. And then finally floating point is making things really good. And now that region drops down to 1/10 of hertz. So in a region where it doesn't matter anymore. But what is also super interesting is that this is not stable. It also depends on where you have placed your poles and zeros. So if you look at some of my loop setups, you might encounter that I have very absurdly precise loop or pole and zero locations. So sometimes you find something like my zero here is placed at 4.104 kilohertz. That actually doesn't matter. The reason for that precision is actually to solve problems here with my digital numbers. So for example, if I reduce this to 86 hertz, then you see that here my low frequency range changes. Okay, it's still below 1 hertz, so maybe it doesn't matter. But when you're, for example, designing a PFC, this is a huge, huge difference in performance. And if you use the save button, then it's a little bit easier. So you can basically freeze that frequency domain, and now you can change your pole locations. So if I go to 86.1 kilohertz, then you see it's getting even worse. So now the roll-off starts at almost 10 hertz, so 10 times higher. And the only thing I have done is changing the location of the poles by 1/10 of a kilohertz. Then I go to 0.2, 0.3. This is where I was, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. And look at this. Now it has improved significantly. And oops, wrong end. So the roll-off now starts at roughly 1/10 of a hertz instead of 1 hertz. So it's a 10-fold improvement. And if I'm, for example, if I'm designing a PFC controller, the important range for the voltage loop would be between 1 and 10 hertz. And now within that range of 1 to 10 hertz, I have an almost flat phase. While when I would choose DCDT generated code, it won't even work. So and that number calculation here, this is one of the improvements that come with the Power Smart version. And I hope that this is really appreciated by customers, but you need to know that this is actually a thing. And
yeah.